Have you ever seen a control system, like a robot arm or a temperature regulator, move past its target before settling precisely? It is a common behavior, and understanding it is key to designing well-performing systems. Determining the percentage overshoot for a system helps quantify this behavior. Percentage overshoot is the maximum peak value of the response curve measured from the steady-state output, expressed as a percentage of the steady-state value. It is a critical performance specification for transient response, especially in underdamped systems. This phenomenon occurs because of the system's internal dynamics, specifically when a system is underdamped. An underdamped system means it responds with oscillations that gradually decrease in amplitude before settling at the desired final value. The amount of overshoot is directly related to the damping ratio of the system. A lower damping ratio results in higher overshoot and more oscillations. To calculate percentage overshoot, you will first need the system's step response. This response shows how the system behaves when a sudden constant input is applied. Once you have this response, either from a simulation or an actual measurement, identify 3 key values. First, find the steady-state value of the response. This is the final value the system settles at after all transients have died out. Second, locate the maximum peak value that the response reaches. This is the highest point the output touches during its initial oscillations. Finally, use the formula. Percentage overshoot equals the maximum peak value minus the steady-state value, divided by the steady-state value, all multiplied by 100%. For example, if the steady-state value is 10 and the maximum peak is 12, the difference is 2. Dividing 2 by 10 gives 0.2, which multiplied by 100% results in a 20% overshoot. Understanding percentage overshoot is not just academic. It has practical implications. In many control systems, too much overshoot can lead to undesirable effects, like excessive wear in mechanical systems, instability, or even safety hazards. For instance, in a robotic arm, a large overshoot might cause it to collide with objects. Control engineers often target a specific percentage overshoot, typically between 5% and 20%, to ensure both responsiveness and stability. This metric is also closely tied to the damping ratio of a second-order system through a known mathematical relationship, allowing designers to predict and control this behavior during the design phase. A related metric is the peak time, which is the time it takes for the response to reach its first maximum peak. By accurately determining a system's percentage overshoot, you gain valuable insight into its dynamic performance. This knowledge empowers you to fine-tune control parameters, adjust compensation networks, or modify system components to achieve the desired balance between speed of response and stability. Ultimately, mastering this calculation helps engineers design robust and reliable systems that perform exactly as intended, without undesirable oscillations or delays.